Hello, hello, hello. So good afternoon, everyone, and namaskar. Okay, so I think this me. So means in this session, what we actually going to see uh neural networks. Okay. So what are neural network? So I will start with the basic mathematical formulation, है ना? So that all of you can be easy to interpret and understand. Okay. Then some network architecture, basic network architecture. Then numerical example using a single neuron, two-layer network, okay, and training process and application and consumption. Okay. So starting with the neural network. First of all, it's a before next slide. First of all, neural network is the supervised algorithm, supervised classification or regression algorithm. Means one of the means application of neural network or any classification algorithm is to predict the fertilizer. Means we have number of depends upon the nutrients in the soil, okay, pH level, nitrogen level, phosphorus level, all this thing. So which type of fertilizer will be suitable? So we can predict the fertilizer type. We will do in lab session. So we can use this neural network for this task also. And similarly for other classification type. In this first case, what we are doing, we are classifying the fertilizer type means based on this soil, what is the appropriate fertilizer we can use. Okay. Similarly, other tasks so is, for example, which type of crop based on this soil nutrition we adopt and we can use. So that so this is the actually the application side. Okay. But in we should know uh, before using an application, we should know how it works. And just brief working so that we can interpret the results. Why these results are coming. Results are coming means what are the classification results are coming. Okay. Okay. So some small mathematics is there. So okay. So let's start with this computational model. Computational model means some mathematical computation is there. So we have to this model incorporate these computations, right? Inspired by biological neural network. Biological neural network means our brain is also having a neural network that is called biological neural network. Okay. And based on this strategy, what researchers did, they designed the artificial neural network. Okay, that is called basically neural network or artificial neural network. So this is the one thing. Okay. So this neural network design is inspired from the biological neural network, which is there in our brain. What second thing is consist of interconnected nodes, neurons organized in a layer. So in next slide, I will tell you this actually some processing is there. Some input is coming, some processing and some output is happening in our brain. Okay. Can learn complex patterns and relationship from the data. As we know, our family members' name, their face, we recognize them. So similarly, this artificial neural network, it will also can uh, learn the complex patterns, relationship from the data, right? And what are the application used for classification? As I discussed, regression. Regression uh, let's say some soil parameters are there and we want to predict what should be the appropriate uh, phosphorus level for this particular crop. Okay. So in that case, there is no classification. There is a regression. We have to predict some continuous quantity, right? So in classification, we predict the discrete quantity. Like for example, there are 5 type of class fertilizers. So we predict any one of them. So that will be classification task. Okay. But in case of, let's say, if we go outside of the soil, this soil environment, if we go, let's say, house prediction, है ना? So based on the locality, based on the number of rooms, okay, and all these things, so we predict the house price. So that is actually regression task, है ना? Because we are predicting the continuous value, है ना? 70 lakh, 80 lakh, 85 lakh, 85.5 lakhs, है ना? Something like this. So that is actually the regression task, okay, predicting the continuous variable. In classification, we predict the discrete variable, right? And pattern recognition is actually the combination of these two, classification and regression. Okay. So one difference means it should be clear that in a neural network, we can perform classification as well as regression. Okay, both the tasks are possible. So small modification we have to do in the network architecture, right? Okay, so next slide. Okay. So the same thing, if we just make the analogy of the biological processing, biological neurons and artificial neurons. Okay. So in biological neurons, if we recall this biological concept about neuron, so dendrites are there. You know? Dendrites, basically the input. Okay. Cell body. Cell body means we have neuron processing cell. So cell body process this input. Axon is the output of the cell body. Dendrites are the input. Cell body is the processing unit. Axon is the output. So what is this synapses? This synapses is actually this input before going into the cell body, before going into the processing unit, it is multiplied or weighted by synapses. Okay. So if I summarize, so dendrite uh, multiplied with synapses weights processed at cell body. Okay. And then we get the output as a F. Okay. So that is. Now this is the biological thing. So almost similar type of concept we applied for artificial neuron. है ना? So artificial neuron means in case of dendrites, we have the input X1, X2, Xn, all this thing. Okay. So first of all, we have to understand this input. Okay. So let's say we have 5 different lands. Okay. So for each 5 land, we have some phosphorus level, some nitrogen level, and some pH level, all this thing. Okay. Moisture level, and some you know, all these parameters are. So let's say we have n number of parameters. So for farm 1, we have X1, X2, Xn. For farm 2, we will also have X1, X2, Xn. For farm 3, we will also have X1, X2, Xn. For farm 4 and farm 5, so on. Okay. So if we have 10 number of farms, then we will have 10 number of inputs. Okay. So what is X1, X2 represent? X1, X2 represent in each farm, what is the moisture level, what is the temperature level, all this thing. Okay, features of the soil. Weights, weights are actually that is actually the thing we have to learn. As a neural network is a learning algorithm. So weights is basically the learning. You know, weight will be learn or we will actually optimize or update. Okay. So what is the criteria for updation and optimization? We will see. Okay, then summation and bias. So just as we know, we have we have this input X1, X or W. I can pronounce as XI, for example, है ना? For simplicity. XIs, where I varying from 1 to n. WIs, where I varying from 1 to n. Okay, so XIs into WIs, then summation, we multiply this. And what this term is, we will see later on in the later slides. Then activation function, activation function, these two things, summation and bias, activation function is basically this thing, processing. Okay. And we got the output, which is there as in the biological case, the axon. Okay. Next slide, please. So now we have to form the mathematics. Because why mathematics? Because this algorithm is mathematically designed, you know, and mathematically W is need to be optimized. So in if we want to program this, you know, we have to program this for practical application. So how we will program, the one of the way is to make a mathematical formulation and then implement this mathematics into program. है ना? है ना? Otherwise, how we will apply this in or use this in a computer, right? So, Z. So what we as discussed, Wi Xi plus B. You know, B is just a bias term. So we will not give too much importance right now, but there is a one term that is bias. Okay, so if we recall our means we all know this equation na is like equation of a line y equal to mx plus c, you know. So y equal y is the this if we plot this x-axis, this is y-axis, then m will be the slope and c will be the this we can say bias, you know. So similar thing is also here. So this, if you see carefully, this also looks like a equation y equal to mx plus c. Okay, y equal to mx plus c, right? But in higher dimension, because x is we know that I varying from 1 to n, right? In higher dimension, this will become a plane. Okay, this will become a plane, right? In higher dimension, hyperplane or right. So this process thing now become this z whatever we are getting is now applied on f. Now what is f? So f is the activation function. Okay, f is the activation function. Now if I just using what we will actually do, let's see. Okay, so black color, right? Okay, so let's say this is x, this is y, or xy, fine. Okay, so if we have two classes, okay, let's say class 1 C1 is represented by plus sign and class 2 is represented by multiplication sign. Okay, and we have, let's say, one farm 1, farm 2, and farm 3 also, farm 3. Okay, and there are some parameters like what is the temperature level, moisture level of the soil, nitrogen, phosphorus, and other nutrients. Okay, so say whatever parameters are here, same will be we have to means compute for this case, you know, and same for farm 3, you know, soil 3 actually, and 3 different. What is our task? Our task is to predict, okay, in these 3 farms, what will be the suitable fertilizer I will use for my next crop. Okay, my task is prediction of the fertilizer. Okay, so assume we have only 2 fertilizers right now. Okay, but let's say simply F1 or F2. Only 2 fertilizers are available to us. Either use F1 or F2, right? So that is. So 3 farms are there. So how many classes are there? There will be 2 classes, right? Because we are predicting fertilizer 1 or fertilizer 2. So let's say C1 is nothing but F1 and C2 is nothing but F2, right? C2 is nothing but F2. So these things are nothing but the samples. Now see, because in this case, we are having X, Y, but so only two features we are considering, right? Only two features means, let's say soil moisture level or humidity level, right? Like this, है ना? Any two parameter. So for farm one, I have to compute these two features. For farm two, I have to compute these two features. Let's say these two, moisture and temperature, and similarly moisture and temperature. Okay. So this axis will be represent moisture and this axis will represent temperature, right? For simplicity, what we can do, we can write like this. 1, 2, and some values, moisture and temperature, some values 2, 3, some values 1, 3. Okay. So, so based on this, so we have to plot these samples. So this thing is called the samples. 1, 2, 2, 3, 1, 3, and so on. This thing will be called as sample. But now the thing is that these things are samples of features, but the thing is that neural network is a supervised algorithm, right? Supervised algorithm means prior to what is our task right now, we have to predict appropriate fertilizer, either F1 or F2 for farm 1, farm 2, or farm 3, right? That is our target. But before we means that is only possible if we know the some prior label or training data. You know, we have to perform, means we have to know some supervised labels, right? Means for some farms, farm, let's say 4 to farm 100. Okay, some farms and somewhere else, you know, which is not related to this. These three farms are different from these 96 farms. Okay, so we have to know what is the uh, means training data for farm 4. What is the appropriate fertilizer, either F1 or F2? We have to do this because this is supervised algorithm. Okay, so I should know what is the appropriate form for farm 4, for farm 5, and so on. Okay, appropriate fertilizer for all 96. Okay, so based on this information and farm 4, what is information is available to us? Only two parameter, na? Moisture and temperature. Empty. Empty for based on empty, farm 4 having uh, means suitability for fertilizer 1. For farm 5, based on empty values of farm 5, fertilizer, let's say 2 is there. Okay. So based on this supervised information, now we use this supervised information and then we actually do the training of the neural network and then we perform the testing on this new samples. I hope this is clear. If any doubt is there, you can ask. है ना? So we have to predict the this this is the test samples actually. है ना? We started with the test samples directly, but to do this in a supervised case, we have to know the appropriate label, means prior label of this, right? So that is the thing. So now we go back to this problem. Let's say two classes are there. Okay, so I am plotting this data for this thing. You know, this supervised label. You know, supervised label means label that farm 4 uses the fertilizer 1 time. Okay, farm 57 uses fertilizer 2 time. Okay. So based on this, I plot all this thing. Okay. These are what? These crosses are basically, this is M value and this is T value. है ना? है ना? So means we plot like this na. This is XY. If we write Z equal to XY. So we plot, if we want to plot Z, so that will be X in this direction. Let's say X is 5 and Y is 4. Okay, Y is 4. So we will move X 5 here and Y here. Correct. So we will do like this. So similarly, for these features of different empty values, different empty values of 96 forms, we are plotting this. Okay, we are plotting. So, and this is for class 2. And for class 1, let's say the class 1 samples are like this. Okay. Now we have to perform the classification. Okay. Classification means I have to make some decision boundary or separation boundary between these two samples. Okay. So what is the first possibility? First possibility is that I can separate these two samples by a straight line like this. You know, this side of the straight line samples are means majorly are there for class 2 and this region classes are majorly from class 1. Okay. Now, what is the use of this boundary or decision boundary? है ना? So, let's say I will take farm 1 data, which is empty, moisture and temperature. So for farm 1, I know what is the moisture value and temperature value. Okay. Or pH value, whatever. You can take any 2 parameter. Because why I'm taking 2 parameter? Because it is easy for me to plot. That's why only. But in reality, we have 4, 5 number of parameters, 10 number of parameters, 15 parameters, depending upon the situation and resources. Right? So now after this is actually the training. In geometrically fashion, if we see this, finding the separation is basically done by training process, right? So if I have to perform the testing, so some new person come, he or she told me I have these M and T values. Please give me suggestion for appropriate fertilizer, whether I should use F1 or F2. Okay, so F1 or F2. So what I will do, if I do it in geometrical fashion, so I will, let's say M value is something and T value is something, and I plot it here, which comes here somewhere here. Okay. So in geometrical fashion, this particular test sample, F1 sample, lies in is which region? In the region of C2. Okay. So my neural network or any classification algorithm will say, okay, based on these decisions, based on condition that above this surface, class C2, below this surface, class C1. Okay. So this particular sample I will assign as a fertilizer 2. Okay. Now my testing is done for F, this particular farm 1. Okay. The same process I will repeat for farm 2 and same for, right? Now, thing is, here the thing is simple, but in practical situation, the separation between the classes may be complex. Okay. So what is the complexity we can have? One particular complexity is like this. In this case, samples are linearly separable. Linearly separable means with the straight line or with the help of plane, okay, I can discriminate. Okay, I can make a classifier. I can discriminate actually, using a straight line. But if my situation is something like this, samples are located like this. So is it possible to classify, make a decision boundary in this case, straight line or something? No, है ना? In this case, what we have to do, we have to design a non-linear, basically the non-linear thing, curve, है ना? है ना? So in this case, we need actually a non-linear separation. So what we will say, in this case, data is linearly separable, but in this case, data is non-linearly separable. Okay. So now, due to this, this particular, if we faces this situation, so we can use neural networks. So what neural network actually does, it is used for linear separation as well as non-linear separation. Okay, it creates decision surface which is uh, which is non-linear. Okay, that is the one of the good thing or advantage, है ना? So if data is non-linearly separable, we can use the neural network. But we don't know actually. If you think practically, okay, some information is some person is coming with some data, labeled data, and this is test data. Okay, but priorly we don't know now whether data is linearly separable or non-linearly separable, right? So what we can do, we actually generally do not go into separation. You directly use some algorithms. For example, start with the neural network and see the performance. We will do all this thing, programming thing in our lab. Okay. So I am just here discussing just giving you the information. So everything we will do in lab, in a lab session. So, okay. So now this is clear. What is the linear separation case and what is the non-linear separation case? Okay. In practical situation, there are some techniques. Okay. By, let's say, one technique is obviously is in front of you. One technique is plot the samples and check. Correct? That is quite obvious. But as I told you earlier, uh, only in this case, only two dimensional features are there, moisture and temperature. But if, let's say, along with moisture and temperature, 8 other parameters are also there. So there are 10 parameters. So we know not uh, how to plot this 10 dimensional thing. Correct? You know, it will be difficult for us. You know, even for it will be difficult for a software also. Okay, any software to plot 10-dimensional data, right? So what we can do is just start with the directly use the neural network and check the performance. If performance is satisfactory, fine. If it is not satisfactory, check the other algorithms. Okay, other algorithms are also there apart from neural network, and then we will make a comparative study. This algorithm gives this accuracy, this algorithm gives this accuracy, this algorithm gives this accuracy, and I will choose the algorithm which will be giving me the best accuracy. Okay, so that is one thing is now is clear. What is linear separation, non-linear separation? Why neural network is preferred? Because if data is non-linearly separable, it also gives good performance. Okay, so now we will come back this home. Okay, so using JET, only linearly separation boundary is designed, but using this activation function f, okay, we applied this f onto z and we will get a, which will actually give me the non-linear, bring the non-linear property actually. Okay, so z is nothing but is a plane. Let's say is like this, is a plane, in a plane. So after applying f on z, what I can get is now a surface, which is can be non-linear, right? Like this. You know? So this thing. Z is straight, plane, hyperplane, but after applying activation function, which is nothing but also non-linear function, so A is now become a non-linear surface. That is okay. Previous slide, please. So Z is the weighted sum. Z is in technical definition. This is mathematically just for completeness. Z is the weighted sum. Why weighted sum? Because X is weighted by W. X is weighted by W, and we will get the Z. Okay. So Z is the weighted sum. B is the bias term. Okay. Bias term. And what is the means general interpretation of bias? Let's say we have plane like this located here in this particular height. So bias means I can uplift it or downward. Okay. Okay. So it just simply lift, right? So B is the bias. F is the activation function which brings the non-linearity, and A is the output activation. Okay, output activation, which is actually bring the non-linear surface. Next slide. Okay, so some very widely used F, which is actually activation functions, are sigmoid function. Sigmoid function mathematically expressed as fz 1 upon 1 plus e to the power minus z. Okay, so this is defined function actually. है ना? So fz equal to 1 upon 1 plus e to the power minus z. What is the range of the sigmoid function? Range of sigmoid function is start from 0. Means it is in between 0 to 1. You can check, you put some value of z, let's say infinity, and then minus infinity. So you will get the range is 0 to 1. Okay, so that is okay. So means from 0 to 1, we can also see that if we make something 0 to 1, so I can, that is nothing but some type of probability, na? है ना? Probability is minimum value of probability is 0, maximum value of probability is 1. है ना? So this type of this property also makes this sigmoid function useful, in some application. Okay, 0 to 1. Then ReLU function is rectified linear unit. Okay, rectified linear unit. Okay, so ReLU is sufficient if just you remember this. ReLU fz maximum 0 z up is how we will plot this. Okay, see, first of all we have to understand this what this means. Now assume, let's say z is minus 5, z equal to minus 5. So what will be the fz? Maximum of 0 and minus 5. Maximum from 0 to minus 5. What is the maximum thing? 0. So what will be the fz? 0. If z is 0, then fz will be 0. If z is 5, fz will be 5. Okay. If z is 1000, fz will be also 1000. Okay. So that is that. Right? So this is ReLU function. Then we have a hyperbolic tangent function that is nothing but fz 10 hyperbolic z range. The range of this function is minus 1 to 1. Okay. The range means the value of f will be in between minus 1 to 1. Okay. Based on application means uh, let's say this ReLU function is very popular. So you can use any function for all the application. Okay, but we have, because we have to update this w weight parameter which we will be going to see, and how this w is optimized or altered means optimized, changed, is affected by. Okay, so I will tell you just after complete this slide, your answer will be automatically there. Okay, next slide, please. Okay, so now we start with the multi-layer perceptron, basically neural network. Okay, so layer types, input layer. What will be the input layer? It receives the input. Okay, I don't know whether it will there. Okay, so input layer receives the input. Okay, receives the input means it in the input layer we have moisture value, temperature value, pH value, and other nutrients value. Okay, so this will act as a input. Hidden layers process information. Okay, in neural network we have hidden layers which process the information like our processing unit. You know, this processing unit is there, so that is. And we have output layer produces the final result, classification, regression. That is key properties. What is the key properties of neural network? Fully connected, uh, feed forward, can approximate any function. Okay, so दुर्गेश इसको नीचे करके इसको ऊपर कर सकते हैं ना? ठीक है. Okay, so what are the properties? Properties are fully connected. Now what all these things are, we will see one by one. See, fully connected network, feed forward network can approximate any function. Can approximate any functions means if I my decision boundary is like this. Okay, this is class 1 samples. Below here class 2 samples. Okay, so this is the actual decision boundary or ground truth. You know? Actual. Using neural network, I have to approximate. Approximate means which is predicted by the network. Okay, so that predicted by network will be something. Okay, so meaning is that it can approximate any function, right? Next slide. Means I request all of you to just use pen or copy because some mathematics is there for better understanding of the. Okay, so start with this. So first of all, what we have given a single neuron, only one neuron is there, right? We will be having some input and some output and some process. So I told you in our case moisture and temperature. So assume x1 as moisture, x2 as temperature, x3 as pH level. Okay, so these three values are there: 0.5, -0.8, and 0.2. Okay, you understood? All of you understood this thing? What is x1, x2? Means meaning is okay. So x1, x2, x3 are the three different features. Okay, attributes basically of the one particular property or something. So weights here. Now I said weight we have to update, but if we update something, we have to start from something. You know? We have to start from something. So some weights are there, which is randomly this we picked. W1 is 0.6, W2 is -0.4, W3 is 0.9. Okay, some weights because we know Z is computed by X size into W i's, right? X size into W. So this okay. Now assume because we have this bias term also. Okay, so assume B equal to 0.1 and very small values are there. And activation function we are using is sigmoid activation function. Just okay, in a previous slide, the sigmoid function is there. So also you write this mathematical expression for sigmoid function. What sigmoid function we have to use? Fz equal to 1 upon 1 plus e to the power minus t. Okay, 1 upon 1 plus e to the power minus t. Means this exercise actually will help you to understand the working. Okay, that is the main motivation for this numerical exercise, right? So bias is done. From up to this knowledge, up to this information, we know we have to compute something like Wx plus B, right? Means x1, W1, then plus x2, W2, plus x3, W3, plus B, which is this. Okay. And the sigmoid activation function we have to use is sigmoid. Okay. So Z is computed. Now we have to compute A. So A is nothing but Fz. So F is here basically 1 upon 1 plus e to the power minus z, right? So the question is calculate the neurons out. Okay. So I will wait for your answer first, then we'll put this. Only thing, just carefully compute this function 1 upon 1 plus e to the power minus z. Scientific calculator, normal mobile computer, 0.9 value of z. Okay. This thing 1 upon 1 plus e to the power minus z. 2.45. Okay. We will wait for one more answer. 0.71. Third answer. 0.71. Okay. So let's come to the solution. Please, next slide. Okay. So calculate the weighted sum. Z equal to in my solution it is in this form. Please just verify. 0.7 something. So Z is I equal to 1 to 3 Wi xi plus b. So we on this thing is we computed this Z is 0.9. Now we have to apply activation function. Activation function is sigmoid version. So A sigma Z 1 upon 1 plus e to the power minus z. Okay. 1 upon 1 plus e to the power minus z. So this thing, right? And you will solve. So it will be 0.7. Okay. So this is the solution of the first one. Okay. Now let's come to the more difficult, slightly difficult problem. Okay. Okay. And consider now, first of all, understand the problem. Right? Consider a network. Okay. Consider a network where input layer is having two neurons. Okay. This is input layer. Let's say this is the input layer. Okay. In last slide, I have a diagram also. Durgesh, can you just go to the extreme last stream? This. So this diagram is also there for better clarity. What we are doing Wx plus B. Okay. So this is actually x1, which is not actually by mistake there. So x1 equal to 0.5, x2 equal to minus 0.8, x3 equal to 0.2. Okay, 3 dimensions. X1, x2, x3, and some bias is also there. So B. Okay. So this is the input layer. I said no, this is input layer. Means this will be the input layer. This is the input layer. This is the bias term which is connected to Y. Y is the out. Means this a processing unit. Okay. So what we do generally, W1 multiplied by 0.5, W2 multiplied by minus 0.8, W3 multiplied by 0.2. Okay. So this thing we are doing and Wx is done plus P. So plus B is this. Okay. So sometimes in many actually majority of the cases, this weight which is multiplied by B is 1. But this weight can be also. So it is in this example, this diagram, it is mentioned point. Okay. So in this case, the Y will be processed this thing. This multiplication plus this multiplication plus this multiplication plus B into this multiplication. Okay. है ना? So that. Okay. So now you know means there are maybe two neurons. So X1, X2, X1, X2. Okay. Hidden layers. Hidden layers means after these two, I have another two nodes. Okay. This first node, second node, and third node, fourth node. Okay. I will draw this. Okay. See. So X1, X2. This is the input layer. Okay. Okay. X1, X2. And in question says two hidden units also. So one, okay. But in our previous question, we have this particular type, this particular structure. How many inputs are there in previous case? Three. So one, two, three. Uh, so this will be X. This will be X1 coming here, X2 coming here, X3. Okay. So the out basically this is nothing but X1. X1, X2, X3. And we have three W's also. So this is W1, W2. Okay. And we have one bias also. Okay. And then we compute the output, which is nothing but A. So this thing we are doing in our first numerical example. But in this example, instead of one and instead of three input, I modified the problem only two inputs, or instead of one, two inputs. Okay. And then we have a final node at the. Okay. So now question is, how many W's are possible here? Okay. How many W's? Which is actually the important thing. W and B are the important thing. Okay. We will come to that. So first W is possible is this. One W. This is another W. Okay. And this is another W. And this is. Okay. So if we name here, let's say 0, 1. And this is input layer. This is input layer. This is the hidden layer. Okay. Hidden layer. Why it is called hidden layer? I will tell you. Okay. 0, 1. Okay. Now I have to name, because I name means I mentioned here W1, 2, 3. So similarly type of this numbering I have to do. Okay. So W is fine. W is fine, but how I will know which W I am talking about? This W, this W, or this W? Okay. So I have to give some number. Okay. So this thing we means it depends. We follow this WJK. Okay. So A, B, C, D, E, F, G, H, I, J, K. J, K, है ना? So J comes first, K later after J. Okay. So this comes first, then comes this. Okay. So based on this analogy, we make the name. Okay. So this thing I can write as 0, 0, right? So what will be this W11? What will be this W? 0, 1, 10, 0, 1. ऐसे राइट. ठीक है. देखिए, it depends. It depends upon the means it is very subjective thing actually. One instructor may use this terminology. One instructor may use instead of this use it W01 or this weight as a W10. Okay, so this is just a terminology you can follow, right? So how many weights are there? 4 Ws, right? So this W I can arrange in a matrix form. Okay, I can arrange this in a matrix form. So matrix will be, what will be the size? 2 by 2. And let's say I arrange this in this fashion. W00, W10, W W01 for W. Okay. Just I'm arranging this thing in a matrix. Okay. So now means how this W comes, that is. And in example, we will also have this another W. Okay. So let's say this is 0. So this will be W00 and this will be W10 if we following this process to W10. Okay. If we following this left to right way, the notation. Okay. But remember, this W10 is not as same as this W10. This W10 is associated with this particular means region, and this W10 is associated with this particular region. Okay. Okay. Now, so this thing I arrange in a matrix form. This thing I can arrange in a vector form because only two things are there. So vector is sufficient, right? So I can write like this: W00 and W10. Okay, I can do this. So now I will go back to the presentation where we assume some numbers, some random numbers of this term. Okay, so two neurons, hidden layers, two neurons, output layer, one neuron, sigmoid activation function. Okay, so we are using the same activation function. Always remember, in the input layer, we do not have to apply this activation because simply x1 comes, x2, all this thing as it is. But in a hidden layer and in the output layer, we have to apply activation function. In this example, we are applying sigmoid. Okay. So in hidden layer, two neurons, one neuron. So which activation function I am using? Sigmoid, sigmoid. Okay. What is the input? I have 0.6 and 0.3. Why this two dimension? Why not 3 or 1? Because input layer is only consist of two. Okay. What is the target output? Okay, this is the input information or process. All this information. Based on this information, I want output as 0.8. Okay. Based on this information, I want output as 0.8. Final output. Okay. So let's start. So start with the hidden layer. So this parameter is given 0.4 minus 0.2, 0.1, 0.7, and some B1 is given, and W2 is given. And take 5 minutes time. Now check in this matrix form, are you able to compute the final value of in next slide? So after 5 minutes, I will show you the solution. Remember the formula? Z equal to Wx plus B. Okay. In first Z, we say Z1, we will compute W1 x W1 plus B1. Just try. बता दें ये तो है ना टाइम चलिए देखें स्टार्ट करें नेक्स्ट स्लाइड okay just previous slide all of you noted down these numbers okay so in copy just after seeing the solution just do in copy also okay so that you remember this and what happens if we do mathematics in a copy pen it is we remember this for longer duration okay so start with this step 1 hidden layer computation okay this is the input layer this is the hidden layer this is the output okay so what will be the output of the hidden layers that is we want to count so what will be the output so because we have two layers hidden layer and output layer so output of hidden layer we called as a z1 okay z1 so z1 will be remember the formula wx plus b now this is wx plus b is for scalar form you know but for matrix operation matrix vector operation the expression will be x into w1 transpose plus b okay this is the notation expression for z1 in matrix vector okay so x into w1 transpose plus b1 just remember this and just put all the values so x will be if you recall 0.6 0.3 w1 is this okay this w1 and transpose of w remember okay w1 and b1 is this okay so if we do all the computation so all this okay. So this thing we just know na 0.6 0.4 0.3 minus 0. Okay so z1 if we just you write this expression because intermediate operation you can skip you know? This expression is fine this is fine this is fine and only then the last intermediate expression you can skip okay so 0.28 and minus 0.0 just you write this value z1 is 2 dimension okay 0.28 and minus 0.0 then if we have if I ask one question if I have a two matrix one is size a by b and one is having a size C by D. I am multiplying these two matrices, A by B into C by D size matrix. So this is possible in which scenario? B equals. And what will be the output matrix size? A times D. Okay. Okay. So this. So next slide. Now we have to remember what is the formula. Z equal to WX plus B. We only computed Z here. So we have to apply sigmoid function also in this hidden layer of. So A1 sigmoid function applied on Z1. So in earlier, if you see, we are applying Z1 is actually the one value, correct? But in this case, Z1 is a vector. Okay. So how to apply this activation function, which is nothing but sigmoid in vector case? So how you will apply? This is the way you can apply. Consider each term, each index as a value and compute. Consider each term as a value and this is clear. Any doubt on this? A11, A1. Okay. So A11 is 0.5695. 812 is 0.49. And remember, if sigma Z1 is a two-dimensional. So if you apply sigma also, the output will be also two-dimensional, right? Any doubt on this? 0.28 corresponding to 0.28, we obtain this value. Corresponding to 0.3, we obtain this. Clear now? Okay, so this is A1. Now, next slide, karte? Both the. Previous slide. Any doubt is there, you can ask me. Can I clarify? Any doubt? Here? Okay. Up to A1, I hope everything is. Is it possible to have? No, vector 2. This is a vector also, but dimension is 2. Even because our network architecture is like that, so we are getting 2 by 2. So if I modified the architecture, let's say increase the hidden node 1, then I will have a different modified matrix. Correct? Means 2 by 3, something like this, or 3 by 2. Okay, I will come to that. Okay, चलिए देखते हैं, सॉल्व भी करते हैं ये डाउट. So in this case, this is the two-dimensional, 2 by, this is two-dimensional input. If we, so practically it is possible, you can incorporate n number of hidden nodes. That is up to the researcher or data analytics. So he or she can incorporate more number of. Okay. So if we incorporate 3, so what will be the size of this W? So obviously 1 W I have to incorporate here and one from this, right? Okay. So this is 2. So based on this, our configuration, we are writing like this W00, W10, and this W, this will be 1, 2. . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 . 2 20, you are actually following this notation, reverse notation, that is also okay. 20 or in my notation 0 2. And this will be W01, W11 and W1. Okay, that is also fine because you are saying the 20 or 21, that is okay. So what will be the size in this case? By 3. Okay, now I will come to the, now your doubt is clear. Okay, so A1 is this, right? Now we come to the next slide. So output Z2, which one? What will be? Slide. Matrix for A1, that is only possible if Z1 is in matrix. If Z1 is in matrix form, you will get A1. Okay, clear? Huh. Huh. In our, this example in weight matrix, I am randomly picked just for illustration. Okay, so this 0.6, 0.2, all this thing. But the transpose operation. Why I'm doing transpose? Means size of the weight matrix. Fine. Okay, okay, that is thing. I followed this particular step. You understood my procedure? Okay. So for understanding purpose, right now you follow this. Okay. But in for more specific case, because these things actually, as per researcher, we can modify as a programmer. As a programmer, if I want to write like this, I can. Okay, but there are some other ways also which you feel comfortable. You can. Okay, so in my case, we say W is this. So W transpose, I have to transpose this, whatever I have. This one. So let's say 0.4 is W00. Huh, from network. Then another notation in row wise, row one. Okay, that's see, this is just a notation. We, if you are comfortable with some other notation, that is also fine. Okay, I am fixing W00 here, this particular weight, where I am fixing here. Okay, and then this particular weight, I am saying, this is 0, 0, 2. Okay, so 0, 2 I am saying. My notification is wrong by mistake. That is fine. That is notification. This is fine. First layer. I am saying, okay, my notation is actually, if I clear this, so this will be 0, 0. If I simply see, this is 0, 0, this is 1, 1, this is 0, 1, okay, this is 1, 0, okay, as per my notation, and if we follow this is 1, 0, 2, W02, this is W12. Okay, this is just because I speak simultaneously, na, so our hand make mistakes. That is now clear. Okay. Huh. On the note, from start with this and then start this. Huh. This particular node connected to all the hidden nodes. Hidden nodes. Okay. Huh. Means if any doubt, means you can write like understand like this. In first way, this is the first input feature connected to all the nodes. In second row, what I'm fixing, this particular node connected to all the nodes in the second. Now clear it is? Okay. Okay. So A1 is there. Now Z2, we have to compute Z2. So Z2 is what? See, please see. Z2 is A1, W2 transpose B2. Okay, same expression we have to use. For Z2, A1, W2 transpose B2. A1 is computed by you already. Okay, A1 is computed in previous slide. Okay, A1 is already computed. W2 transpose is again, I am just making a random number, means some random values. So W.5 and 0.6. Okay, so transpose, if the transpose version is this actually. Okay, and then B2 is 0.2. Okay, so now if we do this expression is clear, first of all. If any doubt, you can ask. This expression, W2 is the weights processed by X. Now, X is what? X is basically become the output of the hidden layer, right? So that's why we are saying A1. A1 is now become X. And then B2 biased. Okay. So now we do all this value, we put all the values and we will obtain Z. Clear? And then output activation function is sigma into Z. No, weight is that is vector. Actually, weight is vector, so you can do the transpose. Transpose is possible, not 3 by 2, and there's 2 by, correct? Right? So then activation function up to Z2 is fine. I hope it is clear. Any doubt is there, you can ask. Z2 is there. Then it is computed. Now we have computed the, after finding Z2, what is the next step? Find the sigma on this, sigma on Z2, so will be y hat. Okay. So y hat sigma Z2 is sigma 0.189, 1893. Okay. We compute like this, 1 upon 1 plus e to the power minus Z. So this value, we solve the expression and we obtain this particular value 0.547. Any doubt in this slide? You ask me, we will go to next slide. Is it clear? Okay, next. Okay, now go. Just see the notes in the first slide. We mentioned some target. That is nothing but 0.8. Correct? What is the value we are getting from the network? The value we are getting from the network is 0.547, which is actually not close to the target. Okay, so this error we are computing using this formula, which is called mean square error. Okay, so mean square error is basically defining like this: half y minus y hat square. Now, what is y? Y is the actual target. Target is 0.8. So 0.8 is y hat. Y hat is what? 0.5471, which is obtained by the net design network. Okay. So 0.8 minus 0.547. Take the square, take the difference, take the square. Mean square error means compute the error between true and predicted value. Take the square and compute the mean. So that is the mean is actually we are saying, okay, divide. If you don't use half, that is also fine. So 0.8 minus this, then half is this value. If you solve, so you will get 0.03198. Okay. Now from this actually the real is the network updation begins. Okay. So what is the result? The network produces output 0.5471 with MSE 0.0319. Any other slide is there? Just please see. Okay. Now go back to this. Now if I ask you up to this much of knowledge, how you will make y hat close to 0.8? What are the possible ways to do this? Changing the weights. What about bias? Can we change the bias also? No? We can change. So the thing is that we can change is W and B. And these W and B are basically learnable parameters, right? Okay. So because we are just randomly put it the values of W1 and W2, matrix and vector. So what we can do, Durgesh, you have to move and for time and time in this previous slide, previous. Okay. So one way is to change this W, where this output make close to 0.8, is changing the value of this W2. One way is this. Changing the value of B2. Okay. If the previous slide before this, then previous. Changing the value of W1 matrix, 0.4, let's say 0.5, 0.3, 0.1, some 0.9, and all this changes. Okay. So what we have to do, we have to change these values of W. Okay. So this is the first, if you see this, you perform the first iteration. In second iteration, you randomly modified the values of W and B. You will get some value, some output, some error. Again, you do this operation, you will get some. So using trial and error, trial, I tried and find some error. Using this trial and error type of thing, you will search, okay, when I will get appropriate minimum value of MSE, right? Okay. So that is actually you have to do in a systematic fashion. What I explained just 1 or 5 seconds before is a non-systematic approach, correct? How many times just randomly all this systematic. So one of the systematic approach is use some algorithm which can update this term. Okay, so that very basic common algorithm is gradient descent algorithm. Okay, so using gradient descent algorithm, we can update this term. Okay, right now some other algorithms are also there in a modern scenario. So start with the gradient descent. So how we will update Wij, this is the code, pseudocode version notation of representing. So Wij is the new weight value. What is Ij? Ij, this is same, W10, 01, 21, all this thing. Okay. So in our example, how many Wijs are possible? 4 in matrix, 2 in vector, 6. Correct? And how many bias are there? How many bias? B1 and B2. Okay? Right? So we have to update these weights and biases. And the formula is this. Okay? New value of W is equal to old value of W minus eta. Eta is the learning rate. Okay? In gradient descent algorithm, eta is fixed, which is the possible values of eta is 0.002 or 5. Okay? Then this function is L here. L is in our case that is MSE. Right? MSE mean square. MSE, then whatever MSE we are obtaining, I have to differentiate this MSE value, MSE function by if I want to update W11, so I have to differentiate with respect to W. If I am going to update W22, then I have to partial differentiation with respect to W. Okay. So in this fashion, all the parameters will be going to update. Okay. So how we have to arrange this in a systematic fashion, in a proper fashion. Okay, all will be updated. Okay, so that approach is basically called this updation is basically gradients. Okay, now there are 5 steps in neural network. First step is forward propagation. The computation of MSE, which is nothing but 0.54 something, is the forward propagation. Calculate error is MSE. Forward, this is the second step, computation of MSE. Backward propagation. Backward propagation means I have to update this W. Okay. I have to update W using this. Update weights, and repeat until convergence. Repeat until convergence means if I make this condition that, okay, let's say MSE, it will be very difficult for me to obtain exact value of 0.8. So I assume if my error is below 0.005, then I will stop. This is my convergence actually. Okay, I will stop and I will use that weight for final. For future test means I will use these optimized weight for future task, means testing the samples. Okay. So forward propagation, calculate error, backward propagation, update weight, and repeat until. Okay. So now if you see in which case this W will be, updation will be almost negligible. In which case, when this particular value is almost 0, close to 0. Correct? Then only we will get new W is all means very almost negligible change to over W. Okay. So when this particular value will be close to 0, then actually my weights will not update significantly. right? So that is the sequence. Okay. So just previous slide, Durgesh. Previous one. Okay. Now let's see the dependency. How this dependency is there. Previous one. Okay. So you are computing this output 0.5471 and then you are computing the MSC. Okay. Now you see the relation. That is the key thing. What is the relation? The value of y hat depends upon Z2. The value of Z2 depends upon the output of the first hidden layer, A1. Okay. Just see the dependency. Z2 value is now depends upon the output A1, which is the nothing but the output of the hidden layers. And previous slide. This particular Z1, okay, then we actually A1 and I forget the chain. So means there is some dependency, correct? Input, then output of the hidden layer, then output, final output. So there is a dependency from output to this output of the hidden layers, right? Okay. So if we optimize this thing, so all the W's will be from starting to end, right? All will be optimized, right? So forward propagation, calculate error, backward propagation, update weights, repeat that. What is backward propagation? Also called in short, back propagation. So back propagation is the using minimization of the loss, and we are doing the minimization of the loss by updating the weights. That is what, and using the gradient descent algorithm, doing the back propagation. Okay. Next slide. So application of neural network. Okay. So application. Okay. Any doubt before going to this application or summarization? True diagram. See. Okay. Huh. Okay. Okay. Let me try it. Right. Explain using this diagram. Okay. So this is the output, and we are getting some MSC. MSC, or let's say loss. Okay. So now see, this is the loss. Take the differentiation. But we know that, okay, we have to take the, if we want to update W this particular weight, so I have to differentiate with respect to W00. If I want to update this, I have to differentiate with respect to W10. If I have to update this W00, then differentiate with respect, and so on. Okay. So first of all, I will update this W. There is no issue. We will update this. Okay. So this thing we can update, no issue, because there is no dependency, right? But this W00 updation depends upon the values used somewhere here. If you see carefully, we obtain this Z1, okay? Because, okay, your W2 is obtained, but output of this is Z1, sorry, A1 or A2, what notation we use. So means updation of this thing, this link also incorporate is not as like as this updation. Because this is not, first we will update W00 this thing, because this particular here, this updation depends upon this updation. Okay. So actually the chain is like this, means you will go, earlier you are doing forward propagation and then you are doing this backward. Okay. This. Okay, but remember and this thing. But remember, updation of these intermediate weights depends upon the previous parameters. Okay, there is one actually formula for this mathematical formula, uh, which actually I not incorporated. Otherwise, and it takes 2 or 3 hours theory session for discussing the uh, derivation of means theoretical backpropagation experiments. Okay. Right? Mhm. Mhm. All the values, all the bits. Uh, Del N, del N, okay. And like we do this now, like for example, we do this y equal to 2x plus 3, and we will write del y by del x, right? In this case, we will obtain what? That is del x. If we recall this thing now, uh, uh, finding the minimization and maximization, take the differentiation, we know the same thing is there. All the weights. Ij is there na? Ij stands for all. Means this thing or this. Forward starts from this. Okay. Initially we give the random weights. Okay. Because we don't know prior any answer. No, no, no. Weight will be updated. See, this is the forward propagation. In backward propagation, W00 now becomes new. Will be there is no new W, right? So this value of this something, let's say it is 2 earlier, after back propagation, it may become 2.5, right? See, so older weight is now neglected. Okay, any doubt? Okay, so back forward propagation, this direction, backward propagation start with this. Okay, and we do this again and again until we obtain some acceptable solution. Right? What is convergence? Finding the sum lowest some low value of mean square. Okay. So if you understood this, majority most of the algorithms work on this. You know, this type of phenomena. Maybe the structure or design is different, but the concept is same. Loss, minimize the loss by updating the parameter. Okay, so computer vision in basically image processing, we can use neural network for image classification. Okay, in soil image also is if we have satellite images of different scenarios, and we can predict that okay, this is the forest region, this is the land region, or something like this. Some basic. Okay, image classification, object detection. And object detection means in war-like situation, what are the positions of the equipments in a neighbor in a enemy country? Okay, so you can detect okay, this is some equipment, this is some equipment, this is some radar, and we do this using satellite image and object detection. Okay, face recognition, recognizing the face. Natural language neural network also used in natural language processing, machine translation. No, we all are using this now, translating. We are giving speech. Text is in a visual form. We can see speech to text conversion. Okay, text to speech. sentiment analysis, chatbot, other applications, medical diagnosis, financial forecasting, autonomous vehicles are widely used in soil agriculture thing, and drones or something. So very popular. You get so using the okay. So summarization, neural networks are powerful computational models inspired by biology. They consist of interconnected neurons organized in layers. Each neurons perform weighted summation activation. Network learn through forward and backward propagation. Can solve complex pattern recognition problem. Numerical examples is presented to understand the concept. Okay. Understanding mathematical formulation, which is almost can follow for other algorithms. Practice for numerical example or some architecture. One question is there now, one increase the one hidden node. So you can modify the architecture also. Okay. Modify the architecture. Learn about optimization. Okay. Any next slide is there? Okay, the diagram is already covered. And some additional remarks which I want to mention about the network. Then we will almost complete this. Okay. So how many hidden this input nodes we can keep in this example? 2. That is fixed. Okay. Because our only we are taking x1 and x2 is our input. How many hidden nodes we can keep? It is up to you. Okay. Try with 2, try with 1, try with 10 lakhs. Okay. Can I keep additional? Okay, this is from this we are computing the loss. Can I keep another hidden layer? Yes. We can keep. How many nodes I can keep in this hidden layer? It is also up to you. Up to you means the thing is that we have to try we have to compute the complete process for this structure. We see the result. Whether results are acceptable, fine. If not acceptable, I will modify the architecture. And this is what I did. I modified the architecture. Okay. So I will check the result again with this new architecture and check. Okay. So general practice is that if your data set is small sized, do not make too complex model. Okay. If data set size is small, moderate complexity is sufficient. If data set is too large, so we have to learn lots of data information and their relation. So in that case, you may require a complex net, right? Okay. Any doubt? Some researchers do this, means some research papers, but the final answer is it is up to it is basically the experiment. Do the experiment with some architecture, check the result, then acceptable, fine. Otherwise, check the another architecture. Okay, but you may find some research actually also going on. People proposes some values. Okay, this number of samples use this set or something, but that is actually the research based. But some as a summary, it is up to the programmer or researcher. Use different architectures and make the decision. Any other doubt? Neural network architecture is the optimization, means optimization of the weights and mass. That is actually the neural network. Okay. Neural network optimization is optimization of the weights and bias parameters. Uh, Such. You means we have to go with this. Uh, some means some advancement are there. If you want to note down, just note down. Some pre-trained networks are also there. So they are just use this pre-trained word, pre-trained networks, in which you do not have to do this training. You use some pre-trained network which is trained for some big data set. Okay, and use them directly to find. Okay, that is pre-trained network. That is called one concept is transfer learning. Okay, this is actually the basic. You know, it means you have seen in my presentation only the conceptual working. Okay, so the motivation for this lecture is that just give you the theoretic means mathematical and theoretical working of algorithm. So once you understand this, other algorithms will be easy for you to understand. Okay, so pre-trained use of pre-trained networks, transfer learning. Okay, and some now CNNs are also there, convolutional neural network. Okay, and now vision transformers are very when we come to the modality, now vision transformers are right. Okay, use of vision transformer in different ways. Okay, so CNNs, now vision transformers, maybe in coming future some other. Okay, and in like in I said, this fertilizer example, one example. Another example is means, some people do research in capture the soil image and based on the image content, um, give some parameters. Okay, this soil having this type of parameter, soil structure, some information about the soil. Okay, like in this crop segmentation, crop segmentation. We you can some modification is required at the last at this stage, है ना? So whether this comes to the classification or regression. Okay, so classification you understood, no? And regression, the difference between these two. So based on application, you can. Okay. So in lab session, we will do one experiment with some data, fertilizer data. We will compare some this algorithm with some. Okay. Okay, Dhruvis, we had time, right? 15 minutes. और कुछ पूछना चाहते हैं आप पूछ सकते हैं लैब में चलिए ठीक है चलो थैंक यू वेरी मच है